In our next example, we have an emu that is being shot out of a cannon 30 degrees above the horizontal with a velocity of 200 meters per second from the edge of a cliff that is 125 meters high. We are asked to calculate where the emu is going to land safely in the valley below. So we should start off as always, if you can, sketch a picture. So here's our cliff side. Okay, so this cliff is 125 meters high. Our emu starts over here and is being launched with an initial velocity of 200, and that is meters per second. And the angle relative to the horizontal is 30 degrees. So as always, we should try to break this up into our vertical components and our horizontal components, and then we can decide how we're going to proceed from there. So let's take a look at our vertical velocities and displacements and everything. So again, as per usual, we're going to say that up is positive and forward is positive. So anything going this way and anything going this way. Those are our positive directions. So that gives us our v1 y, so the y component of our initial velocity, starts off at 200 times 30, the sine of 30 degrees, which is 100 meters per second, and that's in the up direction, so positive 100 meters per second. Our displacement, so our net displacement, is going to be negative 125 meters because it's going down 125 meters down from the top of the cliff to the bottom of the ground. So we have some ground over there. And of course, we have the acceleration due to gravity, which is negative 9.8 meters per second squared. Let's take a look at our horizontal components as well. And then we'll decide what kind of math and what equations we're going to use. So horizontally, all we have are v1x. So that's going to be 200 times, oh, that should be cosine of 30, which is going to give us 173 meters per second. And that's positive because it's in the forward direction. So given what we know, we're going to try to relate everything through time as usual. So we're going to start with our vertical components, and we're going to end up using our equation that says our change in displacement is equal to our initial velocity times time plus 1/2 of our acceleration due to gravity times time squared. We're going to plug in our values from the previous slide. So that's 125 meters, but negative because it's down. Our velocity was positive. Our acceleration due to gravity is negative, and we're left with time squared. So again, we have a quadratic. So if I rearrange this a little bit, so that is in the form ax squared plus bx plus c, I'm left with negative 4.9, and I'm going to omit the units just for a little bit of clarity here, t squared plus 100t plus 125. So of course this is this part here. I've just simplified it a little bit. So based on what we have, you can try to factor this. It's not going to work out nicely, so we're going to use a quadratic formula. So we have t. Now normally your quadratic formula is x equals, but because this time our variable is t, we're going to write t equals. And just a reminder that this is your quadratic formula. So that's why it's important that our equation here is in the form ax squared plus bx plus c equals 0, so that we can plug in to our quadratic formula successfully. So that leaves us with negative 100 plus or minus the square root of 100 squared minus 4 times negative 4.9 times 125. And that's all divided by 2 times negative 4.9. So go ahead and do that, solve for your quadratic formula. You end up with two values, 21.6 seconds and or negative 1.2 seconds. So obviously we can't have a negative value. That's not going to work. So that's no good to us. So that's our time. We can then take this value for time, and because time is going to be constant throughout um, our work here, right? We can use this value of time and plug it into our horizontal components to figure out how long it takes for, or how long it's going to take for the EV to land, and then obviously we can determine where it lands. So our horizontal component, we're just looking for where it lands relative to the cliff. So that's going to be dx equals vx t. Now, of course, in the previous slide, we solved for vx. Since velocity is consistent in the horizontal component, there's no vx1, vx2. So our velocity was 173 meters per second. We have our value for time, 21.6 seconds. Note everything's positive here, right? Because we're going forward. That's going to reflect in our answer. So 3,736 meters, but let's use a little bit of a more useful unit here. So 3.7 kilometers, and our direction, because it's all positive, is forward. So the emu lands 3.7 kilometers in front of the cliff, or forward relative to the cliff.